SpaceX just stacked Booster 19's oxygen tank in 18 days. The previous booster took 128 days for the same work. That's 7 times faster, and it's not luck. Elon Musk cracked a production code so powerful that China's entire commercial space industry is now racing to copy the same architecture, the same recovery systems, even the same chopstick towers. But here's what they're missing. What's the real secret behind this speed revolution? And can anyone actually replicate it? Let's break down what's actually happening at Starbase, because the numbers tell a story that goes way beyond just building faster. Ship 39 has been fully stacked for over a month, waiting for cryogenic testing. But SpaceX didn't rush it. Instead, they built Test Tank 18, a dedicated structural test article designed specifically to validate Block 3 upgrades before risking Ship 39 itself. Think about that decision. Delay your flight schedule to test a separate tank first. Test Tank 18 went through 2 brutal cryogenic cycles, pushed to extreme pressures that characterized strain behavior and established failure margins. Now it's being removed from the test stand, mission complete. What does it mean when a company chooses to validate designs independently rather than learning from flight failures? Here's where the speed becomes obvious. While Test Tank 18 was being tortured, Booster 19 started assembly in Mega Bay 1. The liquid oxygen landing tank moved in first, the specialized tank that supplies propellant for the final landing burn before tower catch. Then the aft section joined the stacked barrel sections, completing the oxygen tank structure. The first methane tank ring arrived Tuesday night, with 2 more rings needed to finish the methane tank before mating it with the oxygen structure. But that 18-day oxygen tank stacking timeline versus 128 days for Booster 18 isn't just about working faster. It represents a fundamental shift in manufacturing philosophy. After Booster 18 exploded, SpaceX publicly committed to having the next Super Heavy fully stacked by month's end, followed by pre-launch testing. They're hitting that target. What changed in their production system that enabled a 7-fold speed increase while simultaneously improving quality control? The answer lies in parallel development paths. While Booster 19 races through assembly, Pad 2 is transforming into an operational launch facility. The orbital launch mount is essentially complete, though scaffolding still surrounds the top deck for final outfitting. The critical installation remaining is the set of protective access doors for the 20 booster hold-down clamp arms. These doors close immediately after clamp retraction at liftoff, shielding internal mechanisms from plume debris and thermal loads. 1 door was installed last week, then work paused. That's not a delay, it's a fit check. SpaceX is verifying dimensions and making minor adjustments before full installation. Why test 1 door when you could install all 20 and hope they work? The water deluge system testing resumed after a multi-week pause, with multiple high-pressure flow tests forcing water through the flame diverter to verify flow rates and structural response. The full activation, where both the flame diverter and top deck spray arrays operate together for thermal and acoustic suppression, will come once remaining launch mount work finishes. Meanwhile, Pad 2's chopstick arms received upgraded hydraulic actuators, replacing original units after testing revealed limits in force output or response time. They're not waiting for failure, they're anticipating stress points before they become problems. Even the ship quick disconnect arm shows this thinking. The arm is structurally integrated and connected to fluid and power lines, but its end section is being outfitted at the production site with mounting hardware before installation. The main quick disconnect interface is being assembled separately near the arm extension. Everything gets tested in isolation before integration. By January, Pad 2 should be operational, with Booster 19's static fire serving as the first real test of both the booster's engines and the pad's infrastructure simultaneously. A short distance away, Pad 1 is being systematically erased. After removing the launch mount legs weeks ago, crews are dismantling the water-cooled steel plate that once sat beneath the orbital mount. Jackhammers, excavators, and cutting torches are removing massive steel sections along with surrounding concrete and rebar. 2 of 7 water storage tanks have been removed and transported to Brownsville's port, likely headed to Kennedy Space Center for reuse. The high-pressure nitrogen tanks that drove water flow are being removed sequentially, followed by all associated delivery piping. The most labor-intensive phase ahead is deep foundation excavation to remove the load-bearing pile system, clearing the way for a new flame trench tailored for future Starship variants. Why rebuild Pad 1 at all when Pad 2 is almost ready? At Massey's, recovery from the ship 36 explosion delivered 2 key developments. The ship's static fire test stand, under repair for months, was moved away from the test site for the first time since the anomaly. Major structural repairs appear largely complete, letting teams focus on flame diverter repairs beneath the test stand position. Simultaneously, the rebuilt methane tank farm showed activity for the first time since being destroyed in the explosion. Extended venting over several hours indicated commissioning tests using inert liquid nitrogen before introducing flammable methane. Engineers are verifying the integrity of methane storage tanks, pumps, heat exchangers, and associated systems under cryogenic conditions. Current progress suggests the site will be ready for Ship 39's static fire test on schedule. Now here's where things get interesting. China watched all of this unfold in real time through publicly available footage and started copying not just the design, but the entire operational philosophy. Beijing leading rocket technology just unveiled Starship 1, marketed as a fully reusable AI-enhanced rocket. They released computer-generated renders showing a vehicle that looks remarkably similar to SpaceX's Starship, except both stages would land propulsively on offshore barges rather than using tower catch recovery. The announcement included 0 verified technical specifications. No height, mass, payload capacity, engine type, propellant choice, or thrust numbers. Just stylized mission profiles showing liftoff, ascent, payload deployment, and recovery. Is that innovation or imitation? Chinese startup Astronstone announced $14 million in funding for its AS-1 launch vehicle, described as a fully reusable 2-stage stainless steel rocket approximately 70 meters tall and 4.2 meters in diameter, powered by methane-oxygen engines. They're manufacturing a test version of the AS-1 upper stage and planning static fire tests along with full-scale ground testing of a chopstick recovery system. The chopstick system is under construction, and its design is visually and operationally similar to Starship's launch tower arms. They're not hiding the inspiration. Cosmo Leap secured funding for its Yukon, or Leap vehicle, again following a 2-stage stainless steel Methalox architecture standing roughly 75 meters tall. They've already constructed a fully functional catch tower and conducted early recovery and drop tests focused on guidance and structural validation, though they haven't progressed to integrated hop tests or orbital demonstrations. Testing of the Methalox engine for the Leap rocket is underway, but the most consequential shift is happening at the state level. China's Long March 9, intended for lunar and deep space missions, underwent a major redesign. Earlier concepts from the late 2000s depicted it as a fully expendable 3-stage heavy-lift rocket. Around 2023, following Starship's integrated flight tests and internal reassessments of cost and launch cadence, Chinese planners pivoted to a reusable Starship-like 2-stage architecture. The revised design stands about 114 meters tall with a 10.6-meter diameter, with both stages designed for propulsive recovery, incorporating aerodynamic control surfaces and grid fins. New methane-oxygen engines in the 200-ton thrust class are under development. Notice the pattern. Most Chinese startups are pursuing scaled-down Starship-style vehicles rather than super-heavy lifters like Long March 9. That reflects practical constraints. Developing a true super-heavy launcher requires industrial depth, capital, and infrastructure well beyond most startups' reach. But copying the architecture is the easy part. Can anyone replicate the execution that enables 18-day tank stacking versus 128 days? This brings us back to Booster 19 and that seven-fold speed increase. SpaceX spent years mastering engines, heat shields, and precision recovery. They developed Test Tank 18 to validate designs before flight. They're rebuilding Pad 1 with lessons learned from Pad 2. They're upgrading hydraulic actuators based on test data, not flight failures. The speed comes from systematic iteration, parallel development, and ruthless validation before integration. China sees the renders, the recovery systems, the chopstick towers. They're building similar hardware, but are they building similar processes? When Beijing leading rocket technology releases computer-generated mission profiles without specifications, when startups announce catch towers before demonstrating controlled flight, when state programs redesign lunar vehicles based on another company's test campaign, what's actually being copied? So here's what China is actually copying: the visible hardware. The stainless steel bodies, the methane oxygen engines, the chopstick arms, the landing legs. All of it can be photographed, measured, and replicated with enough funding and engineering talent. But Booster 19's 18-day oxygen tank assembly versus Booster 18's 128 days? That's not hardware. That's organizational DNA. It's the decision to build Test Tank 18 before risking Ship 39. It's upgrading hydraulic actuators based on test data before they fail in flight. It's moving the static fire stand away from the test site only after structural repairs are complete, not when schedule pressure demands it. It's rebuilding an entire methane tank farm and commissioning it with inert nitrogen before introducing flammable propellant. SpaceX isn't just building rockets faster. They've built a system that learns faster, iterates faster, and validates faster than their failures can compound. That's the 7 times speed advantage, and that's what you can't copy from satellite photos or public webcams. China will build their Starship lookalikes. Some will fly. A few might even land successfully. But will they build them in 18 days? Will they validate designs with dedicated test articles before flight hardware? Will they catch boosters on their 5th attempt or their 50th? The renders look identical. The execution timelines will tell the real story. If you want to track who actually closes that gap, you're in the right place. Hit that like button, drop a comment with your prediction on when we'll see China's first successful tower catch, and subscribe to New Space Review so you don't miss the moment it happens. This race is just getting started.